What's up, everybody? Today now we are going to talk about something called static output feedback control, of course for RTL systems, right? And I think that video will be one of the most important, subject that I covered over the course of, I guess, maybe 7 months or something. Yeah, all right. Okay, let's try to focus on this here. Static output feedback control. All right. And really important subject, right? Really important subject. Because first of all, let me give you a quick disclaimer. You cannot solve this like generally for any type of dimensional problems, right? You cannot solve it because it's NP hard. Meaning, if the dimension of your problem is like higher, basically just forget about it. No way you are able to solve it. All right. So basically the program definition is this. Just give me A, B, C matrices of your, ABC matrices of your plant, and then I'm going to, and the idea is that give me K such that A plus B K C is Hurwitz, meaning the close up, right? Like you can also say A sub CL, A close up, right? The close up system matrix is Hurwitz, meaning all the eigenvalue, like real part of the eigenvalues, right, lie on the left hand side of the complex plane. All right. I mean, for a given ABC matrix, give me a K such that A plus BKC is Hurwitz. I mean, at least this is one of the problems. It is easy to ask, right? It is easy to describe to other people, right? And they don't need to be control engineers or something. But for higher dimensional problems, it is like impossible to solve it. All right. However, there is some hope, right, for CISO, right, single input single output, and MISO, right? I bet you didn't know about this. Multi-input single output, right? And also SIMO, like single input multi-output systems, right? But for the input side or in the output side, you need to have only one channel, right? Meaning for CISO, MISO and SIMO type systems, this problem can be this problem can be considered as, or we can be constructed as a type of BMI problem, right? And again, let me tell you, a problem being a BMI doesn't, it shouldn't make you think, oh, it's easy then. No, it's not at all. It's not easy at all. It's not convex, right? And it will be, you should be very happy if you get a solution from a BMI, especially for higher dimensional problems, right? BMI is just a name, but BMI is not LMI. When you have LMI, you should think, okay, it's like convex and it's easy. All right, done, right? You should be happy. But you shouldn't be happy if your problem is, your problem can be constructed as BMI. You shouldn't be happy. But let me tell you, you should have at least a little hope, right? And another something to emphasize is that if your problem, on top of that being an LMI, if your problem is also kind of a 3, 4, 5 or something dimensional, you should have a little bit hope, and you should be kind of happy, right? Because there is a chance at least you get a solution, right? Okay, so this is a BMI in nutshell, I guess, right? Of course, I didn't explain anything, but now we are going to explain that subject, static output feedback control subject, through a, I guess, very motivating and simple lower dimensional example. All right, first of all, this is our example. This is our plant, right? A, B, C. B is 0, right? And okay, this is our A matrix, system matrix. This is our input, and this is our output matrix. Okay. And by the way, I mean, how many inputs, how many outputs we have? We have, first of all, single input, right? Single input, all right? And since we have like 2 rows in our C matrix, we have 2 outputs, right? Okay, that's great. Okay, what's the characteristic of our plant? Which is, I mean, it is SIMO. Why? Single input, multi output. Okay, because we have 2 outputs, right? And so since our plant is one of those 3 type of systems, so we can construct our problem as a BMI, bilinear matrix inequality type of problem. Again, non-convex, but at least there's some type of hope, you know. I mean, it's 2022, right? So technology has progressed a little, right? And okay, so here, this is the K matrix, right? Here, when I'm talking about the K matrix, I mean this object, right? And let's call it y1 and let's call it y2, right? And as input, your basically control law is k1 times y1 plus k2 times y2, right? Okay, just, I mean, this is like this should be the dream of every control engineer. Just give me the output and I am going to, you know, just multiply it with some numbers and then feed it through this plant, right? And I will hope that the closed loop will be stable, right? This is because this is the easiest controller law, right? What is the other, by the way, what is the other option? Is to, you know, design a some state observer, right? And also, and then maybe some design a state feedback control law, right? AQR or something. Or you can design some dynamic output feedback like H infinity or H2 or something, right? Control law, right? And again, if you have some type of parameter uncertainties, you can also try to construct a mu synthesis type of controller, right? But it's not easy, right? I mean, it's easy, but it is not easier than this controller, right? Just, which is, mean, just multiply it or scale your output signals and, you know, sum them up and then feed it to the system, right? Okay, it cannot get easier than this. All right, so okay, all right, so this is our problem. Okay, and in the previous video we have talked about Hermite Fujiwara matrix, and I'm 100% sure I'm pronouncing it wrong, but okay, let's, you know, go through with this. And in the first video in this playlist, hopefully this will be a playlist, right, today, and we talk about, what was the name of it, blanking. All right, yeah, Bezoar matrix, okay. And okay, and this is, again, you know, it's important because this is a French name, right? Okay, and all right, so what we have learned in the, you know, Hermite Fujiwara matrix, what was the, you know, main takeaway? For a plant, okay, extract or construct the characteristic polynomial, okay, and from that polynomial the variable will be s, right? The indeterminate, I should say, the indeterminate of that polynomial is s, okay? And from that characteristic polynomial, right, construct something called Hermite Fujiwara matrix, and which is a matrix, right? And if that matrix is positive definite, right, your system, it can be, again, system, when I say system, it can be a plant, it can be a closed loop, etc., right? You get the point. Your system, right, will be stable if and only if that the corresponding Hermite-Furgevara matrix, which is derived from computed by using the characteristic polynomial of that system, right, is positive definite. Okay, it may sound, kind of messed up, right? But it is not. It's not. I said it's, but it's not, right? And it is very easy. It's very easy. And however, don't think that you can do, like when I say even for lower dimensional systems, don't think that when I say easy, I mean the process is easy. I'm not saying you can do that every time. Maybe your system is not output or static output feedback stabilizable. Maybe your system, I mean, it is not mathematically possible for you to do that, right? And then of course your BMI solver will return, hey, infeasible or something, right? Hopefully, or maybe it is not a good BMI solver, and maybe it will, throw an error. Okay, but when I say easy, I mean straightforward, right? At least you know what to do step by step. At least you know what to do. Okay, all right. So this is our plant. Okay, and maybe like to look at this to visualize the closed loop. Okay, and this is our control law. Okay, all right. And I feel like there is some mistake in this. Yeah, I should wait a sec. Yeah, that's kind of wrong, because we are not multiplying, we are not negating the output, we are just adding it through. Okay, right. So this should be the, and maybe if you are really into this, let me plus, right, and r equals 0. I don't know what's the point, but in the books they tend to draw it like that. All right, so what's the general idea? This is our plant, this is our control law, this is our controller, and K1 and K2 are the controller parameters. All right. Okay, first step, let me call it step 1, and get the characteristic polynomial, of the closed loop, by the way, right? I mean, I don't, all right. Okay, all right. What is the characteristic polynomial formula, right? General, like determinant of this expression, right? Okay, and you can also name this as a closed loop of the, I mean, a matrix of the closed loop. Okay, all right, or the sim matrix of the closed loop. Okay, all right. So this is the characteristic polynomial, and the answer it, or the characteristic polynomial of this, the closed loop, right, is this. Okay, and don't never trust me, right? And let's go to Matlab, and let's just clear the screen, etc. Okay, this is our A matrix, this is B, and this is our C matrix. Okay, all right, let's print them on the screen. Okay, great. And then since we will have K1 and K2 as our control parameters, right? We are parameterizing our control by using this this K matrix, right? Each entry is K1 and K2. All right, and since characteristic polynomial, right, and we will have S as our indeterminate. All right, and it says real, but S is actually not real, but for the sake of computation. Okay, we are going to construct our characteristic polynomials, right? Okay, this is A plus B K C, right? B times K times C. Okay, which is, you can consider that as A sub CL, closed A matrix. Okay, and S times I, and I is like identity, right? And determinant of S times identity minus A closed loop. Okay, so right, that's it. I named it as a Q of S X, sorry, Q of S k. Okay, why? Because this, the characteristic polynomial of our cross loop mean, first of all, since this characteristic polynomial will be s, and also k1 and k2 will be the variables in our, I guess, polynomial, right? Okay, so that's why I named it like that. It is not only a function of s, but also k1 and k2. Okay, great. So let's run it. Okay, I think you are able to see this. All right, this is our characteristic polynomial. Okay, that's great. And at this point, you can, I guess, describe or state the problem as find k1 and k2 such that this polynomial for those k1 and k2 specific, fixed values, right, is stable, meaning the root of the roots of this polynomial, right? And we are talking about, of course, the CT, continuous time stability, right? Not DT, discrete time stability. We are talking about continuous time stability, and the polynomial being stable in the continuous time sense, right? Is that the roots of that polynomial should lie on the left hand side of the complex plane. All right, that's great. Again, easy problem to state, but not easy to solve. All right, okay, and maybe for better visualization, you can use this, just print the coefficients. Okay, all right, so let's again maybe keep that in mind, right? Maybe pause it and just write it down somewhere or something, right? Okay, let's go back to our tablet. Okay, here, so this is our characteristic polynomial. So I use Matlab to come up with this characteristic polynomial expression. All right, and for the facilitating purposes, okay, I also named a0, a1, a2, and a3, right? The terms that are in those brackets, okay, and why a1? Because this is a s, s, and why a2? Because this is s squared, right? Okay, and why a3? This is s3, right? S cube, all right. And okay, at this point, now we are going to implement what we have learned in the previous video, which is Hermite-Fujiwara matrix, right? And through, for example, what was the general idea for a polynomial, right? There is something called Hermite-Fujiwara matrix, right? And if that matrix is positive definite, our polynomial is stable, right? Hurwitz polynomial, right? Okay, a polynomial being stable, a matrix being stable, right? A dynamical system being stable, the linear LTI system being stable. They kind of have that type of relationship, right? There's some type of connection there. Okay, and the corresponding, this is characteristic polynomial, and the corresponding Hermite-Fujiwara matrix is this. Okay, we can construct it like that. And why, and that's why I name it like a0 to a3, right? Name it like that, because I'm hoping if you watch the previous video when we talk about Hermite-Fujiwara matrix, at the end of the video we determine that type of, like, you can call formula maybe, right? Some type of corollary. Okay, and for this polynomial, okay, and our indeterminate is s, okay, for this polynomial the corresponding Hermite-Fujiwara matrix is this, and there is an if and only if connection. If this characteristic polynomial is stable, or this characteristic polynomial is stable if and only if this Hermite-Fujiwara matrix, this matrix must be positive definite. Okay, and since, for example, 2 times a matrix being positive definite and a being positive, I mean, they are kind of equivalent statements, right? So we can just multiply or divide it by a positive number, right? Okay, so we can just divide it by 2, each entry we can divide it by 2, right? So just to make things, I guess, easier, right? So there is 2 in each entry, you can see, right? So divide it by 2, and so it kind of boils down to this matrix being positive definite. Okay, we can again last time we can state it, the general idea by using Hermite-Fourier matrix, but this is the Hermite-Fourier matrix. This is not right. Okay, but this characteristic polynomial of being stable is stable if and only if this matrix is positive. And if you look at the terms a0, a1, these are the parameters of our plant, right? I mean, they are not linear, they are not appearing affinely or linearly in our entries, in the entry of our matrix, right? This matrix. But they are appearing in bilinearly. Okay? I don't want to say quadratically, but yeah, bilinearly. Okay? And there is some hope again, because this problem is a type of BMI problem, right? And for lower dimensional systems, and also on top of that, if your plant is a type of plant that can be static output feedback stabilizable, which is a mouthful expression or a good property of a system, right? And there is a chance that you can find those parameters a0 to a3. Okay, all right, but these are the coefficients of S, right? Okay, and for our control problems, this a0 to a3 terms, they will also have, right? They will also have k terms. Okay, right? Okay, or I mean, I just written this here to that place, and then substitute there, substitute to explicit forms. All right, okay, so let's, for example, let's a0, a0, a1. Okay, this is a0, a1, this is a0 here. Okay, and this is a1, a sub 1, right? Okay, and this is again a sub 1. All right, so if you check the the math checks out, right? I haven't made a mistake over there. So basically this matrix should be positive definite if and only if our closeup is stable. All right, or this matrix is positive definite if and only if our closeup system is stable. All right, I should say it like that. All right, so basically we have transformed our I guess determining, I mean, wait a sec, computation of our control parameters. We structured that problem, and in a way also you can say we have reduced our problem to a type of BMI optimization problem, right? Now we are going to try to find K1 and feasible K1 and K2 points such that this matrix is positive, right? And this is again a BMI problem, BMI, bilinear matrix inequality type of problem, optimization problem. Again, not convex, but there is hope, and especially for this problem because it is not high dimensional, right? And if our plant again is a static output feedback stabilizable, there is a big chance that we are able to find those K1 and K2 control parameters. All right, that's great. I'm just repeating the same thing over and over again. Okay, just to drive the point across. Okay, and so just question is find K1 and K2, okay, such that, by the way, I shouldn't say Hermite-Fourier matrix, actually Hermite-Fujiwara matrix is 2 times this expression, right? Such that this matrix is positive definite. By the way, I'm not saying positive semi-definite. It is a strict positivity, right? Must be positive definite. Okay, so let's go back to Matlab. This is a optimization problem that we can use YOLMIP, and also for you need to have an BMI, binomial matrix inequality BMI solver, right? You can use pen BMI, or what was the name? BNB, I guess stands for branch and bound, right? And BNB BMI solvers, right? Okay. What Mosaic doesn't work for that, unfortunately. All right. Okay, this is the expression, or this was the code that we used to, generate our characteristic polynomial analytically, symbolically, right? Okay. So what's this? Okay. Again, at Mosaic and YOMIP, and also I should say at a BMI solver. I should say like that. Okay. All right. Let me just get this right. Just look here, right? Just this is like, yeah, almost 20 lines of code. Okay. All right. So right. Okay. So again, we define our K1 and K2 variables, right? And again, you need to, add your STP solver and BMI solver and YOMIP, right? We define K1 and K2. Okay. These are the decision variables, all right? And F is the, you remember, the object that we stack our constraints on top of each other. Okay. And this is our H. Okay. Wait, let me show you again. Show you control down. Okay. This is I called H. Okay. This matrix. Okay. This matrix should be positive definite. All right. Let's go back to Matlab. Okay. This is that matrix. Okay. I just typed the same thing. Okay. Okay. All right. And this matrix must be positive definite. And again, you cannot say strict positivity. You cannot say that strict positivity 0, but you should say, greater than or equal to some little small positive number times identity. Okay. All right. H in positive constraint. Okay. This kind of corresponds to that constraint. And you also impose that type of box constraints on your decision variables, right? I mean, it is a kind of a sensible thing to do. Again, I mean, we don't know, by the way, K1 and K2. Maybe K2 is like 10,000, right? We don't know that. But it would be a good starting point to, impose that type of box constraints. All right, that's great. And then again, our SCP settings, right? We are defining, or we are stating what our solver, right? And BMI BNB is the solver, or pen BMI, right? These are BMI solvers, right? For example, I am sure that you are remember with Mosaic or STP-T3. Those are the solvers that we use for our STP problems. But this is not an STP problem. This is an BMI problem, right? So for that purpose, we need to employ BMI solvers. Okay. All right. And if you have YOLMIP, BMI BNB comes with that. Okay. So you should probably have that already. Okay. You don't need to install something, right, from scratch. Okay. And on top of that, this is our, objective. Of course, you don't need to have that. You can just, write it like that and as a feasibility problem. But I just wanted to, state some type of objective and minimize that term. By minimizing that, we are kind of imposing that, hey, imposing the idea that, hey, try to be economical, right, when generating the input signal, right? This is like the, I guess, in a sense you can say it like that, right? Okay, so let's run it. All right, let's run the optimization problem. Again, this is a different type of optimization problem, right? This is not convex, this is not LMI, right? And at the end of this, you know, iterations, or these iterations, we have our K1 is almost like 3, right? And also our K2, right? Almost like 42, right? And okay, so basically the result is that you can use these K1 and K2, these values, as your output feedback stabilizer, okay, or stabilizing control algorithm. Okay, and byproduct of this computation and all those operations, right, is that you also know at this point, what you know is this: your plant, your original plant, P of S, right, your original plant is a type of plant that can be static output feedback stabilizer, right? Unlike the, or I mean, it is a very, I guess, interesting constraint or property, right, for your system to have. I mean, for example, we are familiar with static state feedback stabilizable type of systems, right? And but that type of systems in that set is a bigger set than this, okay, right? I mean, they are not that comparable, right? But yeah, you get the idea. And these type of systems are not common, to be honest with you, right? But if you have, you know, a CISO, MISO, or SIMO, wait a sec, CISO, let me check my notes, and let's get back to our tablet, right? Again, if you have CISO, right, and MISO or SIMO type of systems, you can construct that static output feedback control problem as a BMI optimization problem. Okay, and that's the main takeaway. And if you're able to find the feasible K values or your K matrix, right, that also indicates that your, you know, plant, your plant is static output feedback stabilizable. Okay, that's great. And I think that's really that was an important video, and I hope you know, get some useful information from that. And that's it for today, and thanks for watching.